Welcome back to ECE 320A. We're in Unit 10, Bode plots, which is covered in the textbook in Appendix E. Homework 10 is due at the end of this unit, and exam number 4 will be coming after we complete Unit 10. We're breaking down the different steps of the sketching of a Bode plot, and in this particular video what we want to discuss is converting a transfer function expression, capital H of S, into time constant form. In the previous video we actually looked at factoring or identifying the factors, and that was then finishing up in pole zero form, and what we want to do in this video is convert that into time constant form. As a reminder, we're trying to sketch Bode plots, magnitude and phase plots, and we're concentrating our techniques or developing these strategies assuming all of our poles and zeros are in the left half of the complex S-plane. So in this video, let's look at converting a transfer function, capital H of S, into time constant form. And really what that means is when you have a linear factor, whether that's a pole or a zero factor or a quadratic factor, again, either a zero factor or a pole factor, we want to normalize the constant coefficients. Here are the constant coefficients in those factors. We want to normalize those to have a value equal to 1. That will make all of these sketching procedures a lot more consistent if we put that coefficient in each of those factors, set that equal to 1, and that's what we want to demonstrate today. So we've start out with this factored form, and now we have the quadratic factor in a standard form where you can now see that this particular term is the omega sub n term. So in fact, our omega sub n is equal to 10. Our natural frequency is 10. We want to factor out each of those constants that I've now highlighted in yellow, and that's fairly straightforward. So let's just do that. We have now 4,000. That hasn't changed yet. We then factor out the 0.1 from the numerator factor. It's a linear factor. And so now we have S divided by that 0.1, so that if we multiplied that 0.1 back through, we would end up with the S plus a 1. And that's all we need to do for the numerator. In the denominator, we leave the S alone. That's okay. But now we factor out the 200 from the linear pole factor, and we now have S over 200 plus 1, and then we can factor out the 100 from the quadratic factor, and now we have S squared over 100 plus 12S over 100 plus 100 over 100, or 1. And now we have our quadratic factor, and we're actually going to write that a little bit differently as we go. But I can sort of hint at that. We know that the natural frequency, omega sub n, is 10, and so we're actually going to not be working with omega sub n squared. We will be working with omega sub n. So let's now look at the different pieces that we've now identified in this transfer function. So we would actually start to simplify this capital H of S. Obviously, we would combine all of the constants. So we now want to know what is the constant in our transfer function when it's written in time constant form. That's the form that it's now in, not yet simplified up, but it is in time constant form because all of these coefficients, constant coefficients, have been normalized to 1. So we now have our system in time constant form, and our constant, which I'm going to now call K, is just the combination of all of these constant coefficients that we've now identified. And we can do this however we want. We could just plug it into the calculator, but let's now do this a little bit more intuitively. We could, well, let me go do the numerator first. So I multiply or take 10% of 4,000. I have 400. So now maybe that's a little easier to think about. I now have 2 over 100. Or 0.02, or to maybe be easier when we start taking the log base 10, we can also write that k, the constant, as 2 times 10 to the minus 2. That's now our constant in our transfer function. We also have our other factors. We have a zero factor associated with a real zero, so it's linear. That's now s over 0.1 plus 1, where the 0 is explicitly identified in this denominator. So now what value of s will cause that to vanish? Well, if s is equal to minus 0.1, that factor will disappear or vanish. So we have a 0 at s equal minus 0.1. If we look again at this transfer function with all of the messy coefficients, we have an s. That's not a very nice looking s, but we do have now a s by itself, so that actually, and it's in the denominator, so it's a pole. We have a pole at the origin. So that's when, well, I should write these as factors. So our pole at the origin, this is now our factor s, and that's downstairs. Since it's a pole. We also have a linear pole factor, or a real pole. And the factor now is the quantity s over 200 plus 1. Again, we can explicitly see, written this way, that our pole is at s equal to minus 200. And if somebody wanted to know what is the time constant, well, now you could see this maybe written as tau s plus 1, so that now the tau is actually 1 over 200 times s plus 1. And so your time constant, tau, is 1 over 200, if you wanted to write it that way. So in this case, tau is 1 over 200. If I write 200 as 1,000 divided by 5, now I can see that the time constant of that pole at minus 200 is actually at 0.005. Hopefully I've done my decimal place in the right location. So now we have a time constant of 5 milliseconds associated with that pole at s equal to minus 200. We're almost finished with identifying all of the different factors. We have one more factor to look at, and that's this quadratic, and it was downstairs, so it's a pole factor. And that pole factor, since it's quadratic, has this standard form of s squared plus 2 zeta, our damping ratio, omega sub n, our natural frequency, s, plus omega sub n squared, the natural frequency squared. If we actually factor out that omega sub n squared, which is what we've already done, then we end up with s squared over omega sub n squared plus 2 zeta omega sub n s, and now it might be easier to sort of write omega sub n squared as the product of omega sub n times omega sub n, and we'll now sort of break that into two pieces. We'll have this piece and that piece subsequently in the next step, plus omega sub n squared, omega sub n squared. I'm just trying to show you where this different structure comes from, and it might just appear like it's magic, but it really is not. So again, we have the omega sub n squared out front after factoring out, in our example, the 100, or we now have s over the natural frequency omega sub n squared, plus, if we cancel the omega sub n's in the first bracketed term in the middle term, we then just end up with 2 zeta times s over omega sub n. So now we have this normalized complex frequency variable s. It's normalized by the natural frequency omega sub n, and the omega sub n squared over omega sub n squared is just 1. Or in our particular case, we ended up with 10 squared, or 100. Then we have s over 10 squared plus 2, and zeta, remember, was 0.6, or 6 over 10. It was the real part over the hypotenuse, or the real part over the natural frequency. Then we have s over 10 plus 1. And that's now our quadratic factor. But remember, in sketching these Bode plots, we want to be able to sort of quickly do this by hand on the back of an envelope. So we are going to be focusing now on an approximation of this. Now this zeta is 0.6. We actually want to just go ahead and almost arbitrarily, but we're rotating those complex components down, keeping the natural frequency the same at 10, and we're rotating those poles to where now they become purely real poles, so that our approximation for sketching purposes will be s over 10. So the approximation, we're going to let zeta go to 1. We haven't changed the first piece. That's s over 10 quantity squared plus 2 times, now the 6 over 10 just becomes 1, and we have s over 10 plus 1. Or hopefully you can now see that as a perfect square. This is now s over 10 plus 1 quantity squared. And maybe it's easier for you to think about as sketching a linear term that's repeated. So that now in our approximation, we are going to go ahead and say, oh, we now have two real equal poles. Where are those real poles located? Well, they're the same distance away from the origin. They are keeping the same natural frequency, and for that reason our natural frequency was at 10. So these are now going to be two poles at s equal to minus 10. And if we can sketch Bode plots for real poles or real zeros, then we just have to do that twice with the same break frequency of 10, and we'll be done with our approximation of how we're going to now approximate in sketching these quadratic factors.